I guess I'll slowly get started. I just got another monitor and also installed Windows 10, so I had to reinstall a bunch of shit on my system. So if anything is off, please let me know. Since I don't, I did some basic testing prior to starting the stream, but I expect some issues along the way. The good news is that I think Windows 8.1 added DXGI. Was it DXGI 1% desktop duplication, which is a sort of high, or 1.2, which is a high-speed path for like full screen mirroring essentially, without the really old school slow way where you get the full screen DDI device context and then do a bit blit, which is super slow, and meant that you know, anytime there's animation on my stream, because I was on Windows 7, it would look super shitty. So hopefully it should be much smoother now. I also adjusted some of the encoding settings in OBS, so anyway, hopefully things will be better overall. Although I do expect some turbulence getting everything kind of confirmed and working. So yeah, um, we've been doing sort of, I guess for the last few weekends, we've been doing a bunch of cool low-level stuff, things not all related to sort of programming language things, but definitely a few things that are in that general realm, like a profiler, um, a CNO, which was this foreign function interface, all these other pieces that are kind of useful if you're writing a whole programming language system from scratch. And so I thought I'd finally just get to an actual compiler, and rather than start with the maybe not the boring part. I mean, I guess it depends on how much you've dealt with before. But if I started with the lexing and the parsing and the type checking, I feel like those parts are they're very standard. Textbooks cover them invariably, probably to excess. But when it comes to sort of native code generation, even though it's really not that difficult, although you have to get your you kind of have to learn a few things about how the computer works, but once you've figured it out, it's not too hard to do that. And then you generate real x86 or x64, you know, machine code, and things run directly on the machine. For some reason, well, I know why, but traditionally in university courses, for example, people will tend to use well, either interpreters if they're sort of in the Lisp tradition, or they will use, you know, bytecode VMs or something like that if they're a little more systems oriented. So yeah, anyway, full disclosure, I do know a little bit about x64, but it's been a really long time since I actually looked at the instruction encoding stuff in detail. So I'm not going to pretend this is completely blind, but it's I'm pretty. Hopefully, I'll start remembering stuff as we start going over the instruction manuals. But yeah, I do have some background. Okay. Yeah, LVM. I think so. By the way, I think an obvious question for this work is like, why am I not using LVM? My basic plan is to structure things in a way that it's easy to put in an LVM-based code generator, but to not, you know, like part of the issue with LVM is that it's extremely slow and bloated. And so I think even for sort of a low-level systems language, it's my belief that at least with the current state of LVM, uh, it makes sense to have a sort of fast native code compiler that just generates code quickly. Some, you know, you can probably make something in that general category that's 10 to 20 times faster than LVM pretty easily. Like in my experiments, that's sort of what I've been able to get without trying too hard. And I think, for example, if you want to do something like edit and continue type features, where you're recompiling like a multi-thousand line source file in like, you know, 10 milliseconds or whatever, something like LVM is not going to cut it. And so and also just for educational purposes, I think starting with a sort of from scratch code generator is a good idea. You can maybe hopefully learn some things. So yeah, what are the sources I'll be using? I think the most authoritative source is just going to be the Intel architecture manuals, and probably some of the OS dev pages. Let's see if I can find those. OS dev x64. This one maybe? Can't remember. Oh, this one. I remember using, last time I did x64 stuff, I used some of these pages. These have some good overviews. They don't, obviously the official manuals have more detail, but this is sort of a good capsule summary of stuff. But yeah, ultimately, I guess the authoritative data is all in here. So I guess a little bit of a preface. My basic plan is to start like I think I announced on Twitter. I'm going to start with just the code generator itself, the emitter. Not anticipating kind of the full range of features of the language. So I'm basically just going to assume for the time being that everything is a 64-bit int and probably unsigned int, and then go from there. So basically, rather than doing it sort of strictly top-down from the lexer or strictly bottom-up from the code generator, I'm going to start with the code generator. I'm going to build in I'm going to start building it out, and then I'm going to build back to the front end. And then I'm probably going to do several passes back and forth so that we will hopefully quite quickly have a complete language, although a very simple one. And then we'll just add progressive layers of features all across the pipeline, not just building a complete parser and then building a complete code generator, but sort of multiple passes. Because I like having things that you can kind of test in a complete way without having to finish the whole program, right? And doing it this way kind of gives you a full compiler quite quickly, even though it's a very simple compiler. So anyway, yeah. Okay. So let's see if I can find the basic instruction coding crap. I guess it's in here. No, that's just the opcodes. Stuff that's hard to remember is all the encodings for ModRM and SIB and all these crazy addressing modes. Where is that? Oh, I guess it's this one. Yeah, here we go. All right. So like I said, I certainly have a general understanding of this stuff. So I can talk about it in some at some higher level, and then hopefully together we can kind of either learn for the first time or recall some of the messy details. But yeah, so x64 is is an extension of the very old x86 stuff. The basic instruction encoding has a variable number of single byte prefixes. Then it has a variable length opcode, and as you can see here, after that there's an optional sequence of possible, I guess you can call them modifiers or extensions to the basic opcode. So maybe I'll create a text file with some assembly examples. So I'll just call this x. So for example, God, I can't even remember half this stuff, but like if you have a simple instruction like this is an intrinsic, by the way. If you have a simple thing like this, and you go look at the assembly, let me just do this. You can see that this debug break intrinsic works out to an int3, which is a software triggered interrupt or a trap. And you can see the encoding is CC and hex. So it's a single byte instruction. So int3 is this. And so that's an example of how, even on x64, which this is, as you can see in the configuration, there are like single byte instructions that have no prefixes and also no no operands or any other extension bytes in the encoding. So yeah, actually one thing that would be a good idea, so we can do some of these experiments along the way, is to, this may be also useful if you guys don't know about this, but you can actually, why is it opening all this crap? I just did a fresh install of Visual Studio 2015, so all the random default crap is turned on. We'll have to turn it off along the way. So yeah, if you if you go to your project, do build customizations, you can turn on MASM. So one annoying regression, I guess, in Visual Studio 2015. Well, actually, I guess it's not 2015. I can't remember when they added it. Maybe it was always the case for x64. There's no longer any inline assembly in the C compiler, so you have to do sort of standalone Microsoft macro assembler crap, which is what I'm going to be doing. So step one is to add it as a build dependency of the solution or the project, and then you have to go to the ASM file. I actually don't know if I mark this, if I rename this MASM, will it actually default assemble? No, it won't. You have to right click and then item type and choose macro assembler. And now it should, yeah, it's complaining. So, okay, now it's compiling. And we can do, what is it, proc assembly test. Proc. Is it not proc? Let me just look up. Let's see. MASM proc and P. Oh, right. I guess you need a label. So something like this. Yeah, that's how you do it. So this should be exported now, and if I do int3 in here, we should be able to confirm. I guess we can just say alright, has to be extra in C. Okay. So yeah, now we should call through here, and you can see, okay, it has a stub, and now we have an int3. Although you can see there's a bunch of padding after here, like an int3 ramp. So maybe that's not the most informative. But anyway, yeah. So I guess along the way I'm going to just write some assembly snippets like this just to confirm my understanding of the different encodings and sort of compare to my manually generated versions. So that would be, I guess, one example. What is it? I think they actually changed this in x64. But it used to be that if you did something like this, and by the way, you can set breakpoints directly in here. So if you do F9 and run, then it should go in there. Oh, okay, I see. So this is now two things. So maybe it's just plain AX. It can't do an x64. Because I want to say that some of the so the increment instructions used to have these nice single byte encodings for the various register operands, and then I believe that they cannibalized those instructions for the rex byte, which is a new prefix you use to encode some extended register operands, among other things. So let's see what happens if I do this. Okay, so that's actually a really long encoding. I guess what this is probably how they get around the fact that the original 1-byte encoding doesn't exist anymore. Oh, and I guess, no, this is a prefix. This is the prefix that switches to 16-bit mode, because now where the default would be, well, actually, so this is a good example. Let's look at these. right. So this 48 is that's Rex. So Rex prefix is 48 in hex. So you can see this is the same same overall instruction, but when you want the 64-bit version of the register, then you have to append this Rex byte. So we'll see that when we go through the instruction manual, but that's the basic idea. And you can see for this case, we have to. There's also sort of an I think it's called the operand size override prefix, but we should go check that now. But that's sort of a way of going back. Yeah, so different instruction prefixes. Most of these we're probably not going to touch. Like there's the lock prefix. There are these for the string instructions, like what is it, like rep move sd. Let's see what that is. Am I right on that? The rep move sd. Yeah, so I'm guessing F3 is the prefix, the lock prefix. Oh yeah, so rep is for F3, so that's the lock prefix, or sorry, not the lock prefix, the repeat prefix. So yeah, that's an example of another prefix, other than the Rex one. Some segment overrides. Let's see, what is this for? Use with any branch reduction. I guess with this, Okay. The segment registers aren't really, except for FS and GS, which are sort of used as pointers effectively, base pointers for things like the, what is it? Let's see if I can do an example. Thread TLS variable. I think stuff like this will go through the thread environment block, but I guess we'll see here. So if I do this and then run, oh. Right. So you can see here there is a move from a constant displacement based off of the GS. So the GS is basically like each thread will have a GS that corresponds to a pointer in memory where a bunch of thread data is stored, and some of the TLS data I believe can be stored in line, some but not all. There's a limited amount of inline space, and I guess that's what it's doing here. The other one we can try, I don't know if this is going to get inline, it probably isn't. No, you call it with another function, so that can't be, that goes through another, has to go through a library. But yeah, but anyway, so that's what segment registers are. They used to be actually like essential before, I guess, 32-bit addressing. People would use this to sort of have more addressable space using these segments. Nowadays on x64, I believe, unless I'm totally crazy, that the code segment, the stack segment, the data segment, I can't remember what ES is. But yeah, these three are like the standard old ones, and those are forced to be 0 on x64, so they're not really relevant. And then some of these, notably FS and GS, are used by some operating systems as sort of like magic registers for things like thread local state. Okay, other prefixes. Operand size override. I think we had an example of that before. What was that? 66. Okay, so 67. I guess 66. Okay. Yeah, so maybe we'll put that in. Rep was what was it? F3. And then 66 is operand size override. And I guess there's an address size override. Let's see if we can. So that's 67. Let's see if we can create one of these. I guess that would be something like is this it maybe? So if I do must be index or base register. I mean, this works, right? But not this. Okay. So what is address size override? Oops. Double click, didn't mean to do that. Right, so operand size, switch between 16 and 32-bit. Great. Either size can be the default use of the prefix selected on the default size. All right. Address size, to switch between 16-bit and 32-bit addressing. I'm not sure, other than using a register indirect address mode, I'm not sure how I can specify like a 16-bit address. And this doesn't seem to, maybe the issue is, well, does this work? No. Must be. Okay, anyway, so I guess I can't see a way offhand to synthesize that prefix, but I guess we'll keep it in mind, although I don't think it'll be relevant. All right, so yeah, opcodes in general, I think we have some examples here, like int3, where the full instruction is a single byte. There's a bunch of other ones like, well, instead of the ink ones, let's do something like this. So in this case, we have the rex prefix because we're dealing with 64-bit instructions. Then we have O3, which would be, I'm assuming, O3 would be add, and then C3 is the ModRM bit. It's basically the operand byte. So so yeah, on the what was I saying? The operand byte, the ModRM field is, if there's ever an operand, there's always a ModRM byte, and it's a little bit of a weird one. So they mentioned here an additional 3-bit opcode field is sometimes encoded in the ModRM byte. Let's look at the encoding. But so ModRM has basically 3 parts. I guess it's normally written like this. It has 3 parts. So it's essentially like 8 3 plus 3 plus 2 bits. And one of them, so the thing to know about the 3 bits is that they can encode 8 different values, which maps to the 8 different fairly general purpose registers on classic x86. And then this last one can encode I guess let's see. Oh, right. The mod is the 2 bytes. Types of modifiers. I guess because of that, maybe it's easier to think of it as 2 plus 3 plus 3. So there's different kinds of modifiers. For example, I think mod equals 0 is direct addressing. So, and actually, so what was the instruction here? Let's just copy this over. So this one, as an example, this one, so 48 is rex, 03 is presumably add, and then C3 is the ModRM byte. And I guess we can try to figure out what the encoding of that would be. So I happen to know that for this instruction, so RAX corresponds to register 0. RBX corresponds to register, it's not register 2. This is one of those stupid x86 things. I think RBX is number 4, right? Yeah, so ACDB. So RBX would be number, this would be 0, and this would be 3. And I think you can already see where the 3 is coming from here. It's actually RBX. And then there's a C, and I believe the C is, it could be a modifier, but I don't think so because this is a direct. Presumably the C is actually because of, let's go look at the add instruction. I think it's because it's using the opcode extension. No, that doesn't make sense. I think because maybe there's a special encoding for add and register operands. So let's go take a look. So 03. Yeah, okay, that's why. So 03 03 has this encoding, so that's what we're seeing down here. No, actually that's not true. So 03 and then C3. And by the way, this -R means that I guess the middle field of the ModRM byte corresponds to a register operand rather than a opcode extension number. I mean, RAX should be 0. Well, we can go and look at those tables we had before for the instruction encoding. Let's see here, ModRM. The mod field combines with the RM field to form 32 possible values, 8 registers and 24 addressing modes. Rec opcode specifies either a register number or 3 more, right? So I guess that's something to. So ModRM, 2-bit modifier, 3-bit register or opcode, and 3-bit register. And well, I guess it's called the RM. Let's maybe do like this. Actually, let's call this X. I think that's what is sometimes called. Mod XRM is sometimes is what I've seen it written, which basically means the X stands for extension. So the idea is that if you have a see if I can find an example of that. There are certain instructions where the opcode byte is not enough to uniquely identify the instruction, but you don't want to use a full 2 bytes just for the opcode itself. And so if you have an implicit first operand, for example, and I think yeah, actually, so let's look at mul. I think that's the perfect example. So if you look at the multiplication instruction, it has an implicit operand. So for example, if I do mul bx, really this means rax is like that. So rax is actually, and there's also, I guess, low. So if you want to be super pedantic, you would do like this. And so because of this, there's no like variable destination operand. There's only a second one. And so because of that, mul, I guess we can verify it here. Mul rbx, let's do rcx, which is actually the second register number. Okay. So you can see we have the rex byte, and then we have f7, which is this form here, because we're in 32-bit mode, not 16-bit. And then you can see there's this /4. The /4 means that this register or extension field is cannibalized for the sake of extending the opcode. And so let's see if we can do the math here. Calculator. God, I don't know if the Windows 10 calculator, does it still do hex? Maybe it'd be interesting to do octal, because a lot of the x86 encodings are actually kind of octal oriented because of the, you know, there's like eight different registers and so on. But yeah, so let's see. Way too high quality. I actually turned up the bitrate. Maybe I should reduce my bitrate. Other people, please let me know whether it's completely over the top with the speed. Okay, let's see here. Why is this shit? Okay. What are we looking at? All right, RCX. So E1 is the ModRM byte. So according, let's just copy and paste that over here. If you go to right, so low bits are RM, middle bits are the register or extension, high bits are the modifier. So I guess actually let's maybe write some dumb code just to start doing some of that stuff. Let's see here. So this would be, I guess we can do it from the other direction. And then we can say, maybe I'll do it like that, which is a little unconventional writing, but I think this is probably good. All right, get rid of this crap. So let's see. if we do emit modifier of 0, Rx of, what was it? Rx of 4, and then Rm would be, what was the thing? I think we did RCX, which is register 1, I think. So let's do that. And then, shut all this garbage down. I haven't set up all my things yet, so let's just look at this. Hex. So supposedly this is 21. Let us see. No, this is E1. I guess I'm getting the modifiers. Oh god, I'm fat fingering all this shit. Oh, I think I'm just an idiot. It's not 5, it's 6. 3 plus 3. I am great at math, apparently. Okay, so that's it. So if you have a modifier of 3 out of 0 to 3, then you get what the encoding we got. So that's consistent. Okay. By the way, if this seems kind of stumbling, it's because it is. Like, I'm not intending this to be an exposition. This is me actually reminding myself, and actually maybe teaching me some things that I probably should have known, but thought I knew. So we'll stumble through this together. Right. So that's the ModRM one. I guess we should have a few other cases. Like, let's do the RIX. Let's do. So the RAX, so this would be, and then B is 0, 3. So if you do this one, you get C3, which, if I'm not totally mistaken, was the same thing we got here. Yep, C3. So you can see that's consistent. So that's the ModRM. We should look at what the different modes do. So this is 16-bit. We don't care about that. This is the normal one without a scale index bias extension. Right, so 11, I see. So 11 is actually direct addressing. So this is direct addressing. This is direct with 32-bit displacement. This is direct with 8-bit displacement. This is just indirect. Or I should say this is indirect. This is indirect with different size displacements. So that's fine. I guess I should make a list of the different register numbers. So RBP, RSI. Why did I start at 0? I'm an idiot. RSI, RDI. And then there is R8, R9, just for completeness, R10. All right. And you can see this encoding, by the way, is consistent across both the rows and the columns. The column is sort of the source, actually not necessarily the source operand. One thing that's a little bit confusing, well, not confusing, but something you may think at first, is that, hey, if you look at some of these instructions, like the one we just manually encoded here, which was this, that was this, whatchamacallit, you might think that, oh, this one, this middle field is always the destination. That's actually not true. It depends. It depends on the instruction. So for example, I guess a good example would be if I do RBX 123, you're dealing with an immediate operand. And immediate operands in x86 aren't actually part of the, they're not part of the operand bytes. They're a completely separate extension on the back of the instruction. And they're not like a special addressing mode or anything, is what I'm saying. They have a completely separate encoding. So you can see that, for example, actually I should keep, okay, I skipped past it. So let me just back up. Yeah, so you can see that add with register operands is 0, 3, and then C3 for the operand. Now you can see what happens is when we have an immediate operand, we get an extra extension byte, and also the opcode itself changes. So it's not the same opcode anymore. So it's like there's a completely different instruction variant from the point of view of the basic instruction encoding opcode map, which is, I guess, useful to know. So in this case, let's see. So this was O3C3. So the interesting thing, you notice that these are the same, even though now RBX, which was the 3, RBX, the 3 went from the RM into the XR or RX. Even though in one case it was source and the other is destination. That's a good example of how you can't count on it being one thing. What typically happens then, I believe, let me think. I guess in this case it uses the other one for an extension. All right, let's see here. It probably means SIB, right? So if I'm using this 11x, in the ModRM. I guess the ModRM, the other part is just 0 in this case. It's not actually used as an operand extension. Yeah, okay. Anyway, so what was that digression for? All right, that was me just commenting on the fact that you can't assume that even if you have, you can't assume that like one given field is always a destination and one is the source or anything like that. Especially with immediate operands, things are usually switched. Because immediate operands, of course, they can only be sources, not destinations, right? So it means that one of the fields is sort of redundant. There's no real flexibility there. All right, so so you can see the ModRM byte through the mod field can do like some basic displacement modes here. By the way, the displacement is another thing that gets pasted at the end, so maybe we'll do that. If I do mod rx and I do, what is it, dword pointer, and I do like rcx plus like this, I guess I can't actually do, I have to use this notation. Must be the same. Alright. Can I actually do that? No. I have to use this stupid notation. If you do this, then what you will find is that you can see the displacement is now a byte at the end. And it's only 1 byte, so there's a special mode. And I guess in this case, what does it say? If it's an 8-bit displacement, then it's 0, 1. Which means we can go and try to replicate it over in the emitter code. And then we have 0, 0 and RCX. Is that 43? Does that look right? I should have probably checked what we... fuck me. 43. This one is 41, so what did we do wrong? So 41, yeah, 41 is right here. I said 43. Oh, it's because, yeah, this is 1. Right, so that's 41. That's consistent with what we were seeing here. 41. So that's a 1 byte displacement. If we have even a 2 byte displacement like this, you should see not 41, but now it actually has to change the mod, so it should be 81. Yeah, I guess that makes sense, because now let's see, it went from 41 to 81, as you can see in this opcode, in this table. So yeah, those are like, I guess the range of kind of addressing modes you can encode directly in the ModRM byte, but there's also, of course, this thing called the SIB, scale index bias, and that's a whole different thing, right? Where when you do, I guess a good example would be if you do something like, let's choose something that's not used. If you do this plus 4 times r dx plus displacement, all right. No. Oh. Right. So in this case, you can see that this whole thing in parentheses is like a special addressing mode. You can see you can see the immediate operands come here, or not, the displacement comes here. I think the 0, 0 is just padding, if I'm not totally mistaken. Maybe I am. So you have the rex byte because it's 64-bit, I guess this is the LEA instruction. And then we have the ModRM byte. And the ModRM byte in this case is going to essentially encode the RCX, but then it's going to say after the RCX there is, well, let's see. So RCX would be here, and then it's going to say we have an extension, which I guess is 0C, no, 8C, 8C. Oh, right, it's because we have this displacement, 32-bit displacement, this 1, 2, 3, 4 hex. So because of that, we are down here, I see. So if you want to have SIB, you, depending on the size of the displacement, or whether you have a displacement at all, I suppose. So for example, I guess, well, let's do a few variations just to confirm that. No variation, and then a 1 byte, or no displacement, 1 byte displacement, multi-byte displacement. So this would be 0C, which is this one. Next one is 4C, which is this one. And then 8C for the 32-bit displacement. I think probably the first part we should code. Okay, I think that's sort of okay, so that's how you indicate that you want the scale index bias. And then there's actually, so basically, let's see, I guess you can look at it basically like this. If the RM field is equal to 100, unless mod is 1, which is 3, you're dealing with a SIB extension, which means the following byte will then be the SIB byte, which indicates, you know, like you can see it on the left actually, what the different modes are, and then the right is the thing you're, well, let's see. So I see the scaled index, and then the other one's the base, and then the displacement comes after the way it would normally do, regardless of whether it's a SIB or not. So I see. So the displacement is actually kind of orthogonal to the SIB. I always thought of it as part of it, but that's actually not true. That's just normal, just like with plain ModRM indirect addressing. All right. Oh, and as for this encoding, it's the same 2 plus 3 plus 3 thing, where the 2-bit is now like a scale. So you can see it can either be 1, 2, 4, 8. And the other ones are just, so why is this? The nomenclature means a disp 32 with no base if the mod is 00B. That's interesting. So if you have a displacement with no base, I guess we can test that. So the base would be this, right? So in that case, I guess let's go over the matrix. So RDX4 would be here, and then it would be 12, no, 95, what was it? No, I don't want to install that shit. Let's see, what was it? RDX, and then RDX4, then 95. Right, so this says we don't have a base. I see, so this is effectively like just saying the base is 0. I guess it does also mean you can't do RBP-based offsets, which I guess we can confirm. So you can't do, I can't do this, apparently. I wonder if this will encode. Really? How is that encoding? I'm pretty sure this is illegal. right? Yeah, this is totally legal. Oh wait, so that's 4C. So that was different, and that's in the ModRM byte. So 4C means 4C. So this is 4C. What about 0Z? That's interesting. Oh, I see. Okay. Still seems wrong. I mean, I guess we can test this, but like, so if we step over, let me bring up the register window. God knows. I have no idea why they look at this fucking thing. It's just like a text window. It's not even in column format. So anyway, let's go here. So RCX should change. Let me go over that. Actually, let me just put some stuff, consistent stuff into RDX. So this would be like, let's call it 1, and RBP is 2. So at least there shouldn't be some random values in there. Okay, so that's 4 plus 16 plus 2. So that is adding. I'm confused about the encodings. Yeah, that's adding in. So this is the 4C. So 4C ModRM 8-byte displacement with RCX as the destination. And then over here we have 95, which is RDX times that. But then this means, oh, only if the mod is 0 does it mean this, otherwise it means that. It's a little confusing. So if you want a plain displacement, it's this, otherwise it's this. So I guess this means, okay. I see. So you can do this, but you can't do but you can't do, so you can do that, right? So that works fine. So this one is ESP. I see. So you can't do scaled stack addressing, which actually makes sense since the stack pointer is always an absolute address. It's not an offset. So doing multiplying by it doesn't actually give you anything useful. Yeah, that makes sense. And then this entry is actually okay. I think that makes sense to me. Alright, so I guess maybe the next step is to write some code to generate, based on a higher level description of what we're trying to do with the addressing modes, generate the concrete code. So like, suppose you have something like this. So you can, I see, so you can do the displacement separately. Emit operand. Let's just think about what would do. So if 8-bit, so let me just think of the decision tree. If 1-byte displacement, if multi-byte displacement, if no displacement. Those are like the three cases. And essentially we choose like that. So I see. So step one, look at the, well, step one, is it direct or indirect? If it's direct, we just do this. It's just that straight up. If it's indirect, then and base register goes in. If indirect, base register goes in RM. Unless base register is RSP, then need, right? Because if it's an RSP, then there's actually no way to do that because the RSP index is cannibalized for the SIB extension. So what are the different... So it seems like there's a bunch of redundant encodings, right? Because all of these appear, with none, appear identical. I actually don't know what that means. It's a little bit confusing. I see. I guess we can see which of them it uses. So if I do RSP, yeah, even this. So let's do a few variations. So let's test the theory. So OC 0Z be the RM 0Z, which is this one, right? Because RCX is the destination and C means we can't encode it in line, even though it's something where, actually I guess we can maybe show that directly. Like if this had been that, it would have been encodable just within the SIB. So yeah, you can see that this one, even though nominally it has the same form, this one, this indirect address can be encoded directly in the ModRM, whereas here it essentially needs an extension. So it has like a sort of degenerate, not quite degenerate, but it has like a seemingly needlessly long encoding. That's kind of interesting because you're doing a lot of RSP-based indexing with displacements. Anytime you're doing, you're addressing local variables or whatever. Maybe that's an argument for using RBP for that. I don't know. But yeah, so RSP, they all have this, and you can see there's now 4C, 8C, because the modifier, this is modifier 0, modifier 1, modifier 2, both of them followed by 2.4. So 2.4 should be, it's this one, but I don't, like, the interesting thing is, in theory, let's see if in theory, 64 and A4 and E4 should all be valid encodings of the same operands here. But anyway, okay. Okay. I wonder, emit direct, operand. Let me just put this out. I think the way I'm going to use this in the compiler, at the point where I call something, I kind of already know whether I'm dealing with direct or indirect operands. So I should, and I don't want to have decision logic in the low-level emitting function. So I think I should probably just have different emitting functions for the different overall branches of the decision tree. Maybe even handling RSP separately, because normally RSP is not a general purpose register, so it's like emitting like a relative stack thing is probably worth getting a separate function emitter function for. So okay, direct operand. In that case, we just have these, and we just do 3 RxRm. Indirect operand. And this is 0. Actually, let's do it like this. Obviously, these are going to be inlined, right? I know some people will probably, like, if you look at some low-level code for something like this, a lot of people will use macros, but I don't think there's really a great reason. You can force inline them if you're worried about debug mode or whatever. But anyway, yeah, so in this case, we essentially just do the emit indirect operand and then emit the displacement as a single byte. In the general case, is 32-bit displacement. I guess maybe I'll make this faster later. Now let's just do it one byte at a time. Actually, that's not right. So this is actually that, and this is that. this is actually wrong because it doesn't work. Well, let's see. Yeah, so this doesn't work when RM. I should write my standard assert macro. Okay, so let's do sib. Let me remove. Let me shorten this. It's getting a little bit unwieldy. Emit displaced indirect. Small displaced indirect. This would be large displaced indirect. This would just be indirect. This would be direct. Let's call this byte displaced. Maybe just displaced. Alright. Okay, so next step. Right, if you have combinatorics are getting a little bit unwieldy, but whatever. Let's just go for it. If you, right, so now, so maybe, actually let me write some examples in front of each of these. I believe this is the other way around. The byte displaced, yeah. So I actually named these wrong. So let's say indexed, mid indexed indirect. Let's see. So if I have emit scaled let's say call it indexed indirect. So there's Rx, there is RM, there is index, and there is scale, log2 scale, and there's index register. I guess I can call it register because C. I feel like I want to call this something else, like I think I call it reg, but that's shorthand. I would rather have something. Okay, let's bite the bullet. Actually, maybe I'll just call this operand. It's probably better. Oh, they're both kind of operands, so maybe not. Let's just do that for now. So this is the displacement. Now we're doing this as indexed, indirect. So same set of parameters, but now index with a log2 scale. And log2 scale has to be less than 4. And actually I should assert that for all of these. Mod should be less than 4. This should be less than 8. This should be less than 8. Actually, let me just do it this way. X1, X2, X4, X8. This will be register. This will be scale. Okay, that's nice. This also becomes more self-documenting, I suppose. All right, good stuff. So emit indirects. So step 1 is we emit 0 because there's no displacement for now. Then Rx, and then the second one should be, I think, RSP. Yep. So I'll just call it 4. And then, right, so now we're in the SIB, and we essentially had to do the same kind of stuff. We're just going to reuse that function even though it's sort of serving double duty now. Mode, let's say this is direct is 3, indirect 0, byte displaced indirect is 1, displaced indirect is 2. But yeah, for this, I'm going to make this like a raw function, so it won't have any types per se here. Right, so this will be scale. Alright, this will indirect. This will be displaced indirect. Byte displaced indirect. Oh, sorry. Indirect. So scale, and then the scaled index. Well, let's see. Right, so this is the equivalent of the Rx up here, which is the first operand. Right, so down the rows is the second field. So this is the base. This one, and that. And I think again here, so you can't do RBP. Or rather, if you do RBP, so what was I saying? Something like that. Okay, so I see. The mode you can't handle with RVP is something like this. So you can do RAX times, you can do something like this, and you can do something like this, but I don't believe you can do this, right? No, you can. So why am I wrong about that? So this is 0z dB. So what is dB? D or D? Yeah, dB. dB. Oh, I didn't mean EBX. I meant IBP. So what is this? ED. Oh, right, I'm wrong about that. Of course, there's this special shit down here. If the mod is... Okay. So now we just need to do the various variations. So displaced, indexed, indirect, well, actually, this should be so sorry if this is really mind-numbing. Of course, I don't know whether I'm doing anything right here. Okay, let's write some example code to correspond to these cases. Indexed, indirect, it would be like this plus, let's say 4 times our dx. This would be RCX plus 4 RDX plus 3, 4, 5, 6, 7, 8. Actually, as a guide to this, I should write something like Rx equals that, operand equals this. By the way, one reason I'm leaving this Rx field as just a plain UN8 rather than a statically typed register is because there are cases where this isn't actually a register, but just, like I said earlier, an opcode extension off the base opcode byte. So trying not to over-constrain or mislead by it. It's also why this has more of a cryptic name. Otherwise, you would maybe call it operand 1 and the other one operand 2 or something, but I don't want to mislead either other people or myself. So, all right, I think we actually have enough that we should be able to, I think I can remove that now. We should be able to take a basic instruction and just emit a crap load of code. So for example, add is 48, let's see, 48 for the rex, 0, well, let's see here. Let's get the template for an add. So it's 4803. Okay. So I guess one thing that would be good to do, as a really basic thing, is was it RDI? Which one is number 8? I guess it's just number 8. And then just do some direct action here. So this would be destination source. Okay. Ugh. This is where I sometimes wish the type system was a little less strict. Or not. I think this is fair. Doing arithmetic on these things is probably not something we're going to be doing otherwise. It's just for testing. So, anyway. Let's see here. Alright, actually we're going to write this out to a file. Was it B? Test bin. I'm going to write it as binary. And then we're just going to do a big old F right of the element size. Emit pointer minus code. And then 1. Oh, source buffer first. Fuck you. I know what I'm doing, guys. Hopefully. Alright. Apparently not. Oh, it didn't open. Oh. Okay. Let's let's try doing some disassembly. Can't assemble for architecture unknown. Okay, obstump. Let's try to figure out. Oh, so small m, not big M. Okay. Okay, so let's call this test.text, and then I'm going to drag and drop this in. I think, yeah, so far so good. I'm just going to take a quick bathroom break. Alright, I'm back. So yeah, I mean, I guess the fact that it works at all means that there's not much chance of any specific case being wrong. So that covers those cases. Let's maybe just wrap that up. Emit add. Let's make sure it still works. So it still works. So let's do some other stuff like by the way, if people have questions so far, not that I'm an expert on this, I'm figuring it out as we go, but you know, please feel free to ask. So that definitely didn't work. Oh, I didn't run it. That would explain it. Okay, so in this case, I see. So that's because I'm actually trying to do something that with this encoding doesn't do what you'd expect. So I think that's fine. So in this case, if we don't have this, we're going to do that. Okay, let's regenerate the disassembly. Oh god, this is fucking AT&T syntax. Let me just figure out how up disassembly Intel syntax. Like my brain is broken. I can't. Okay, here we go. Intel. I really can't like mentally swap those things. So, all right, this is better. This is more like Massim syntax as well. Okay. So yeah, that looks right. And then for okay, so this one's wrong, which is very interesting. I see. So for RBP, yeah, so for the RBP indirect, I'm clearly fucking it up. I think that's a case where I have to use the SIB in order to do that, but I thought that was for ESP. Oh, I see. So this one denotes... Oh, I see. So there has to be a displacement following that. Oh, that's very interesting. So indirect with RBP as that indicates a 32-bit displacement with no operand, so just a pure displacement. Meaning we actually have to do that too. And then we need something to cover this case. Which is just, this is called emit displaced. Mod Rx RM indirect Rx RBP. Actually, let's make this RSP because that way the certs are sort of consistent between these two. Where is the displaced? And then emit for displacement. So now we should get it a cert. Yep, okay. I guess the interesting case about this is we can still, if source is RBP, you can still do them. You can still do it. You just have to. Well, I guess the way to do it is something like this. If you do an emit indirect, I was saying I was not going to put the decision logic in the functions, but the way you do it is, if this is RBP, then you have to emit a 0 displacement. I think that actually works. Why is this rip relative? Added to the index. What index? Maybe this is just, I mean, I know that rip relative addressing. Let's go to another website, the OS dev website. Okay, so why the fuck did they say that? I mean, that's fine, I guess. Maybe I'll make this a pseudo register. No, I really shouldn't. I don't want to have that decision logic in a compiler for the basic emitters, so let's stay true to that principle. I think that is the right approach. And then, and probably not actually this, and then we'll just have so what was this? Oh, that was actually a typo. Oh, right. Yeah, sorry, that was not a typo. Displaced rep. Displaced rep is actually, yeah, like that. And then Rx. No, that's not. Okay, so there's only really one here. Hey, what are you writing this with? I'm not sure I understand what you mean by with. I mean, it's C++, I'm on Windows, Visual Studio, etc. Okay, so we skip the indirects for RSP and RVP, but otherwise this all looks good. Okay. We should do that for, and actually rather than displaced indirect, I'm pretty sure I should have called that just for the operand order to be consistent, indirect displaced. Because then displaced is last and the displacement argument is last, so that's oh wait, no, this fucking thing. Like displaced. Oops. Index indirect byte displaced. Indirect indexed byte displaced. Yeah. Indirect index displaced. Alright, so indirect byte displaced 0, 1, 2. Oh wait, so we still need this plain one. Byte displaced 0, 1, 2. Okay, let's see if this works. Yep, that works. Oh, I guess I should also test the version where add the source and destination are flipped. So I'm doing the 03 variant. If you want the RM to be on the other side, so instead of 03, it's 01. What should we call these? This would be add, it's like flip. I don't know. Add reversed. Let's just try to flip everything. Right, so now the source and destination are flipped. And that looks good. So we can just go back to what we had before. Okay. I guess let's do some... What's the next step? So that was indirect byte replaced. I should also do a plain displaced, emit displaced. Which would... Is there only displaced, or is there also byte displaced? No, only that, so... Oh, this is the rip relative. I guess that's where I was wrong, wasn't I? All of this stuff is rip relative. So why did I not emit displaced? Yeah, I kind of should have seen that, shouldn't I? Indirect displaced. Okay. Okay, that's fine. Although I only got that here. How often do I get rep? Oh. Skip the 4 here. Probably not my best idea. Alright, so that was it for directs. Let's do... let's also do indirect indexed. So destination, source, and let's just do index. I guess we can use destination again. And then x4 just to have something. Does not take 4 arguments. Does it not? Oh, displaced. Let's just do this one. Indirect indexed. Okay. Okay. So the thing being scaled. So emit RSP indirect, and then the rest. So the base is this. So the operand clearly I omitted those in the wrong order, because in this situation I would expect RDX to be the index, which it isn't. So these are reversed. I guess maybe I should emphasize that this is the base to be consistent with the normal terminology. And actually, let me do that for all of these that are indirect. Okay. So now the thing being multiplied is the destination. Okay, so that's how I expected. So the base is the thing varying. So indirect, indexed, base index scale. All right, it's getting to midnight. I think I have 35 minutes or so before I probably go to bed. But so let me figure out if there's anything I want to do I haven't done. Honestly, this is a little bit further than I was expecting to get tonight, since I didn't really know if I would actually get to write any real code or whether I would just be reading shit. So this is pretty good. One glaring hole is that I kind of split out the add from the operands. Now the problem is in x64, the rex, we haven't talked about these R8 through R15 registers. On x64, these are basically, an obvious question that should raise to you is like, hey, I thought we only had 3 bits for the operands. How can we encode these? Well, basically, the idea is that the lower 3 bits are encoded. So R8 would have the same lower bits as RAX, R9 would have the same lower bits as RCX, but then the higher bit, if it's set, is encoded in the rex byte. So actually, I said the rex byte is 48 in hex. That's actually not true completely. So let me show you an example. Compare this with R8. Actually, let me set it before so I can see both disassemblies. So yeah, you can see it's 48 here, but now it's 4C. So essentially, you get an extra, there's some extra bits here for the operands to extend. The problem is the way I've sort of broken this up, you kind of have to know that by the time you emit the rex. I think probably what you should do is what is it, like R, and look at the rex byte. There's like 3 different bits. So there's 3 different possible register operands, right? If you look at what is it, indexed, there's 3 register operands. There's Rx potentially, there's base, and there's index. So we need up to 3 extension bits. I think they're called well, let's find out what they're called. Is it like I thought it was RW and X, but it seems like W just refers to the basic 48 byte. Let's see here. Okay, rex prefixes. Here we go. Specify operand size. Specify extended registers. Not all instructions require yada yada yada. Right, so RXB. Let's see here. 0, 1, 2. So we do, we essentially do this, right? Well, let's see, what's the easiest way to do it? So lowest bit, extension of the RM, base, or opcode reg field. This is the index and the reg. I see, so actually base goes lowest, then the index, and then the rex. Something like that, I guess. We should probably have a version for the common cases, like this would be that one. Okay, so I think these are probably the 2 cases. So these should not include that in line, and instead, so actually let's step back a little bit. I would suggest. Let's just do the direct ones and make sure we're handling this correctly. Alright, let's remove that shit again. Alright, so if we do nothing, absolutely the same shit should keep happening. So in this case, we should just do destination and source. So let's see if that gives the same results as before. Yep, that looks right. So it's 48. Now let's expand. Let's go up to the higher ones. Let's see what happens now. Okay. RM less than. I see. So we should mod them at this point, I believe. We should still do it assert for 16. Okay. So far so good. And you can see we're now getting, it's 49, which means we're getting these R9 through R15. That looks great. And if we go down the end, we should see the same shit for the destination. Yep. So far so good. So that means the basic stuff works. Let's now do the index counterparts, I suppose you'd call them. Huh, I wonder when you do emittrex destination, I wonder if it matters what you emit for the second part. Let's try that. Cannot convert. Okay, that looks right. And what about this one? Yep, that also looks right. Okay, out of curiosity, let's try to make this one. What will happen? I think in theory it should still work because it's underspecified, right? So that's interesting. Did that actually do anything? That doesn't make sense. Why didn't this change? Let's try removing that. Oh right, it gets shifted, so it would have to do something like 8 to see a difference. Oh, but that is actually... Okay, so that actually doesn't change anything, right? So those parts of the rex byte are just inert for when there's no second operand. I guess the same is true for the index part of the rex byte. Alright, but 0 seems like the reasonable thing. So that's it for this, and then for this, we need to do the same basic crap. Oh, except we now have an index rex. problem to have. Oh, so I know I'm getting tired. So we're getting that nice extension. Let's go down here, R15 plus. Yep, that looks right. So it's both handling the extension for all three register fields, which is great. Alright, this is pretty cool. I think this is all we need for the code emitter. I guess that's not totally true. Some of those cases, like the RSP offsets, well, as long as we do it manually. So for example, if you do, so I can't do this. I can't do all of this stuff. But what I can do is like, is it emit indirect or emit indirect indexed? And then RSP. And the other one, I believe that was like if you, no, yeah, so if you parse RDP here, it actually doesn't matter what you pass, because it's going to be treated as 0. And for this, we just need let's see if that works. So we should be able to see. Okay, so this rex, okay, that's obvious garbage. So that's definitely some crap here. Let me just verify that that's it. I didn't screw up anything else. Okay, so that was the issue. Yeah, so the issue is emit indirect. Oh, emit rex indexed. What did I do wrong here? Because we already have RSP plus. Oh, that's the wrong one. RSP plus. So we already have that with in that example. Okay, let's go look at the encoding tables. So RSP is the base, and none is if you pass RSP. So that should be the case. It doesn't matter what the scale is. So that's confusing. If the source is RSP, then destination source. Like if I do RAX instead, I'm pretty sure this is just gonna work. So I don't know why. No, even that doesn't work. This is and it doesn't even make sense because these are all 0. Clearly I'm doing something stupid here. $48.04.04. There's a Rex, there's the operands. Oh, I'm a fucking idiot. That's the answer. Okay. Right, so this is how you do you emulate the indirect mode using a SIB. Okay, so that works. What about indirect mode with RBP? So you can do RBP plus something. So if you want to do RBP with nothing, I think it's because RBP is almost always used with a displacement, so they just cannibalize that for the RIP encoding. What if you want to have a pure displacement there? My guess is that on x86, this field here, they say it's a pure displacement for the effective address. Since there's no RIP relative addressing on 32-bit Intel, I'm assuming this was redefined to have a different meaning, and maybe, I mean, so what happens if you do okay, and then you do, well, actually, let's not even do it here. Let's do it in assembly. Move RAX. Well, I think this is. so add, this is pretty long, so I see, so there's a sib. You have to use a sib to encode a pure displacement. So 0, 4, 0, 4, alright, so 0, 4, and then a pure displacement. What? No? 0, 4. 0, 3 for the add, 0, 4 for the ModRM with a sib extension, and then 25, which is, I see this one, none. I see, so this specific case is the pure displacement. Gotcha. So we should probably create something specific for that. Emit direct. So base is RBP. And then for this, it should be RSP. And then you emit the displacement. It displaced. Illegal use of type as an identifier. How is this different? Oh. Okay, so this DS is just saying data segment relative, but that's always implicit. Unless you have, I guess, segment overrides. So yeah, that does look correct. So it's RCX, okay. Okay, instead of calling this add, let's call this add register. And call this add memory. have to do it in the other order, otherwise things fuck up. So emit, add reversed. Emit, add memory. Well, 5 minutes left before midnight, so I think I did what I wanted to do. Last thing was, yeah, supporting the full 16 registers on x64. I think we have all the addressing modes, quite a variety. Let me just add a comment here. And yeah, so that's pretty cool. I think from this, once we have this, actually writing sort of a machine code compiler will be, almost trivial. Like, you have to go and look individual upcodes up in the manual, but this is how you do it. It's pretty good. So yeah, anyway, I think I'm going to wrap up. So this was mostly supposed to be a test, but I actually ended up writing a bunch of code, and I guess pretty happy with where I got. So if you guys tune in tomorrow, I will start the project proper, and hopefully we'll give more exposition and background rather than just sort of a low-density research stream like this one. So yeah, if any of you are still around, thanks for hanging out, and I'll be back tomorrow, probably 10 a.m. PST. So yeah, have a good night.